So, good morning, everyone. Thanks for being here. Hi, nice to see you. My name is Maarten Mulders. I work at a Dutch company called InfoSupport. We consider ourselves to be the sauce that makes your food even better, so hence the awesome sauce. But today I'm going to talk with you about GraalVM and how you can build your own DSL on top of GraalVM. So just to have an idea, who has already been working with GraalVM? Who has heard about GraalVM? Let's start with that one. Okay, we're at Devoxx. It's hard to not have heard about GraalVM, I guess. Who has been working with GraalVM already? Done something with it? Really, no one? I'm surprised. Honestly, I'm surprised. Well, at least to each and every one of you, you probably learned something new today, which is good. So let's get started. Let's get started first with DSLs, domain-specific languages. Domain-specific languages are a specific kind of languages that can be run by a computer, by a machine, but they are targeted at a very specific domain. Often it's a business domain, but that's not always the case. Let's look at a few examples. This is a domain-specific language. What is the domain for this language? Who is using this? And what are they using it for? Anyone? Sorry, excuse me? SQL query, yes, exactly. It's targeted at database users, and it's meant as a means for them to interact with the database, to retrieve data from it, to manipulate data maybe. So very narrowly targeted at one specific domain. Another example. What would be the domain for this language? Excuse me? It's Cucumber, exactly. That's the name of the language, BDD. Yeah, but that's the process. I'd say the domain is specifying system behavior. So if I want to describe what a system does, given a situation and given an action that I'm doing, I expect the system to behave in a certain way. And that's what this language is targeted at. Mainly testers, maybe functional analysts or something, but people who want to describe what a system works. Now, these are both very technically oriented domain-specific languages because we know them. We might even use them as software engineers. How about this one? This one came from a talk I attended a year or so ago, and the person talked about a fictive, a made-up company, Wolf and Sheep Limited, which is a company that transports cabbages using boats. And you might know the puzzle, you know, if I transport the goat, then the wolf will probably eat the sheep, which is not good. So they had a developer make a domain-specific language which allows them to solve their transportation problems. This one's based on Scala, actually, and it runs on the JVM, but it requires you to have at least a very primitive knowledge of Scala, because the language is described, the language is actually designed in such a way that the Scala compiler can make sense out of it. So yes, it's targeted at business users, but well, they need to install Scala and they need to have at least some basic knowledge on how that works, writing code, running it, etc. One more example. Does anyone recognize this language? Brainfuck, exactly. Very good. Oops. This is the preferred way of writing Brainfuck, by the way, which means no comments, not too much white space. Sometimes even the spaces are omitted, but for readability, I thought it would be a good idea. And as much stuff as you can put on one line, preferably. What is the domain for this language, one would say? Well, there's actually two domains I can think of. One is impressing your friends and coworkers. Like, can you really do this? And the second domain would be making your brain explode, because it's really hard to write a program in this language. A less preferred way is this, where you group statements together in lines and you add comments to your source code, but yeah, who does that anyways? So if you present it like this, it's at least a little bit more easy to understand what the program does. just a simple comment that describes what it actually does. For example, it adds two numbers together and prints out the result. And in the right column, you'll see all kinds of comments like this is how we interact with the memory that we have available. Now, how does the memory look like? In a Brainfuck program, you have a very simple memory structure. It's just an array of bytes, and there's usually 30,000 items in the array. That's all. Some implementations have smaller memory or bigger memory, but it's always one array of bytes. Bytes are initially 0 unless you modify them. And you have one pointer, and the pointer just tells you where you are in the array, at which item you're currently pointing, basically. The language has 8 commands. So there's a command to increase the value that you are currently looking at. There's one to decrease the value you're currently looking at. There's one to print the current byte that you're looking at to standard out. And there's also one to read one byte from standard in and store that at the current location in the byte array. There's also conditionals. So if the current value equals exactly 0, we jump to the first command after the matching square bracket. And the other way around, if the current value is not equal to 0, we jump back to the corresponding opening square bracket, and then the first command thereafter. And finally, we have 2 commands to move our pointer through the byte array left and right. That's all. Now you might say this is very small. This is a very small language. It has just 8 commands. The memory layout is very simple. It turns out to be rather hard to program in this language. So yes, it's easy to implement, but it's hard to actually use it. But the language in itself is Turing complete. Who knew? It's Turing complete. That basically says you can write any algorithm in this programming language. You can mathematically prove that. On the other hand, it's also a Turing tar pit, a lesser-known category of programming languages, which basically says, yes, you can implement any algorithm in this language, but it might not be a good idea to do so. You might actually drain yourself in very complex things, and your brain might explode, for example. So much about domain-specific languages for this moment. The funny thing is, you can run a Brainfuck program on the JVM using GraalVM. Let's look at a quick demo for that. Here's a simple Spring Boot application. As we can see down there, it runs on GraalVM 19, which is currently based on Java 1.8 still. Java 11 support is underway, but it's not yet there. And this program is very simple. It allows our business users, so as to say, to write their program. Everything in Brainfuck, by the way, which is not one of those 8 commands, is considered a comment. So I can just write English text here, which will be considered a comment. And I can ask the web application to actually run it. And it will tell me that when I add 5 and 2 together, the result is 7. Well, that's not exactly rocket science. But what is rocket science is what happens under the hood, because our program was not interpreted by Java or something. It was actually run on the same compiler as the Java source code does. And that basically is rocket science, and we'll see why. So as I said, this is all made possible thanks to GraalVM. Now, GraalVM is a research project by Oracle Labs and the University of Linz in Austria. One of the things that they aim to achieve is to have one virtual machine to rule them all. This is a project targeted, for example, at language implementers. A common problem when you want to design your own language is that you first start writing all kinds of tools to interpret the source code and to transform the source code into machine-readable code. Then you have just-in-time compilers, and ahead-of-time compilers maybe, which basically duplicate lots of knowledge from the first part, because that's all semantics about how the language works. But it's needed to have a performant runtime. And once you have that, that's the first time you can actually prove that your language is working and it's actually interesting to end users. Because as long as there's no good runtime for your new shiny programming language, who's going to use it? No one will. They'll just sit and wait until, well, I can actually run those programs. And as long as that's not possible. So there's a huge investment to make before you can actually start using a language. Now, GraalVM is actually a bunch of components, and you might have seen this picture before. GraalVM builds on top of a regular stock Java virtual machine, and it adds a few components. It adds, for example, the substrate VM. Now, the substrate VM is a very tiny virtual machine, and it's used when you build, for example, Quarkus applications, and you package them to a native executable. Then the substrate VM is added because, well, there is still some kind of stuff that needs to be done, but you are not using the hotspot VM anymore. You're using the substrate VM, which is very limited in what it can do, but it's also very tiny and very fast. Now, one of the main things there is the GraalVM compiler, which is another compiler for the Java virtual machine. It can compile Java code, and it's written in Java itself. This is opposed to the hotspot VM, which is written in C. If you attend a talk by Chris Tallinger, I know he's around these days, he'll probably explain you why that is, but the GraalVM compiler is actually faster than the Java compiler written in C. That's a strange thing, but it is. And then there's Truffle. And Truffle is a layer on top of the Java virtual machine, which is there for you to run dynamically typed languages, interpreted languages, on the JVM. And using Truffle, you cannot only run Java. We were, of course, already able to run Java on the Java virtual machine, but you can also run other languages like Ruby or JavaScript on top of Truffle, on top of GraalVM. Now, as you might see, this one is not completely, this one's a bit blurred, the GraalVM compiler. We can actually use Truffle without using the GraalVM compiler. So if we design and implement our language on top of Truffle, we can package that and ship that. And someone who does not have access to GraalVM can still run the program. It will just run slower. Or at least that's what they told me. It might run slower if you don't have access to the GraalVM compiler. Well, if people say it might, I want to know if that's indeed the case. Of course, Brainfuck is not a dynamically typed language, but still, I created a benchmark. There's a program there's a whole archive of Brainfuck programs on the internet. One of them is called japi.bf, and it's yet another pi calculator. So the program does a lot of calculations, which is interesting for benchmarks, and it calculates 15 digits of pi. If you run that on a stock hotspot-based Java virtual machine, you'll on average have 53 milliseconds for each operation. 53 milliseconds, and there's a plus or minus 1 error in that. So it's pretty constant, 53 milliseconds. Now, if you run it on the GraalVM virtual machine, we see that the time drops to 45 milliseconds. So each invocation, on average, takes just 45 milliseconds instead of 53. Again, the error is plus or minus 1, so it's pretty constant, which means, basically, that we have around a 10% increase. It runs about 10% faster this time. Okay, I was curious, would this also work if the calculation becomes even more complex? I modified the program a little bit, calculating 45 digits of pi instead of 15, and still the same pattern appears. On a stock JVM, average execution time is 207 milliseconds per operation, and on a GraalVM, it's 185. Still, that's around a 10% increase in speed. The errors are still pretty low, 2 or 3 milliseconds each. So yes, your program might indeed run faster if you're using GraalVM. And later on, we'll see one of the reasons why that is. But one of the things we first need to talk about is Truffle. You saw this big bar in the diagram saying Truffle, but what actually is Truffle? Truffle is a library which allows you and me and everyone to build programming languages. It's targeted primarily at dynamically typed interpreted languages, but you can actually run other languages on it as well. And you do that by giving Truffle an AST. We'll see what an AST is, but for now, let's just say it's a bunch of POJOs, plain old Java objects. And those Java objects are annotated using the Truffle API, so Truffle knows about the semantics of each of those objects. An abstract syntax tree. Well, this is just a very small part of the abstract syntax tree for the program that we just saw. An abstract syntax tree usually looks like this. There's a root node, because it's a tree-like structure. And for each step that needs to be done when executing the program, you create another node. And the node contains the implementation. It contains the steps that need to be done at that specific point. It's called abstract because many concrete details from your source code are not in here anymore. How was the indentation? The AST doesn't know. Did you use brackets or not? AST doesn't know. Did you use curly braces? AST doesn't know. It's abstract in the sense that this is what the machine is going to do. Now, imagine that you have written your program and you've been able to compile on AST out of that. Truffle will start running your program as if it was an interpreted program. So that's down there. It will just run through the AST, perform all the instructions that are in there, and at one time it may decide, hey, this is code that's provided by the runtime. In our case, that's the Java virtual machine itself. So it will switch to runtime code. It may also decide that some code is better to be compiled to native code. And it can switch from interpreted mode to compiled mode. This compiled machine code is like the very lowest level you can get. This is machine code, highly optimized, very compact, but also a lot of details that are in the interpreted code, like type checks and all the like, they are not there anymore. So that basically means Truffle needs to do some assumptions on your code. Let's just think that, in this case, the variable will always be an integer. It will not be a long. It will not be a string, for example. And again, your program can jump back and forth. It can run a function X or function Y. And that machine code can also turn out to be invalid. So maybe one of those assumptions wasn't true. And we can jump back to, for example, interpreted mode, where the interpreter takes over and says, okay, I did this assumption, and it turned out to be wrong. I'll do another assumption, or I'll just run in interpreted mode from here on. Now, by the way, this might sound relatively simple, but don't be fooled. This is actually state-of-the-art research. And if you dive into this, you'll often find yourself not reading blogs, but reading academic papers in order to understand how this works. It's pretty cool stuff, actually. And it allows languages, like, for example, it allows certain languages like Ruby or like JavaScript to run faster on the JVM than they run in their own native environment. And a lot of my coworkers who I tell about this are like, how can that be possible? You add another layer of abstraction, the JVM, and the program runs faster. How is that possible? And that's exactly why this is so fascinating, this technique. One of the tricks that they apply to achieve that is called partial evaluation. This is a technique that actually originates from the mathematics world. If you have had at least a very tiny bit of mathematics, it's relatively easy to understand. Say we have a program, a small program, it's called f. It takes two parameters, x and n. And it will calculate x to the power of n, given that there are positive integer values. Now, the program can be described in a mathematical way as such, if if n equals 0, the outcome of this part of the program is 1, which does make sense. X to the power of 0 is always 1. Now, if n is even, we could say, well, actually, x to the power of n is equal to x to the power of half n, and then multiplied with itself. That's what it says down there. Fx half times n to the power of 2. That's also a mathematical rule, right? You can just say that the exponent divides by 2, and then multiply it with itself, and that would be the same outcome. And then finally, if n is not 0 and it's also not even, then the program is x to the power of n minus 1 multiplied with x. Also basic mathematical rule. And this describes how we can calculate x to the power of n for any values of x and n, given that they are at least positive integers. Now, partial evaluation says, let's make an assumption. Let's try to reduce the complexity of this program. Let's just say, for example, that n equals 5. Now, if n equals 5, our program becomes a lot simpler because we can actually fill in some of the blanks, right? If we do that, we find that fx, n's gone because n's 5, it's a constant now, is reduced to x multiplied with x to the power of 2 to the power of 2. So a lot of complexity and checks that we needed to do there in the first version of the program were actually removed by making assumptions and by removing complexity and saying, well, this is just 5 and this is not a variable anymore. Now, as I said, this is something that mathematicians have been doing for ages, but you can also apply this process to your program and the data that your program processes. So I could just say that if I have a variable somewhere in my source code, the language does not allow me to tell whether it's a number or it's a string or it's something else. I can just say, let's just make an assumption, let's just say that it's a number, and simplify my program quite a bit, run it, and see if it works. And if it does not work, then, well, okay, my assumption was wrong. I'll do it again, but I'll add all the type checks and stuff. Now, partial evaluation starts with the root of your AST, and it just traverses the whole abstract syntax tree, and it tries to visit every node in the program. And even for simple programs that run on the JVM, this AST can actually be pretty big. Because, for example, if you do things like printing a value to standard out, did you ever dive into what that means? System out print line. There's synchronization, and locking, because you don't want to have two threads writing to the same output stream. There's all kinds of type checking, and then finally this one byte gets written to an output stream. We never see that. We just do system out print line, and we're happy with that. But under the hood, there's a lot of things going on. If we would have this partial evaluation run our whole program, the size of the program would explode because all this complexity would be in there. It would probably be easier if we just let the JVM do that, because that code is already highly optimized. I don't think we can scratch off even a nanosecond from that. It's been there for 20, 30 years? No, 20-something years. I don't think we're going to shave anything of that. So maybe we should just let that be there and not even try to apply our partial evaluation there. And that's what we call a boundary. That's where we say to Truffle, okay, it's all nice and well that you are doing your partial evaluation, but here it stops. We're not doing the partial evaluation beyond this point, because beyond this point, it doesn't make sense to do that anymore. The program would be too big, and it would take too much time to actually do it. So that's boundaries. And how do we do that? Well, somewhere inside our AST, we have a Java class which does the period, the dot. Remember, that's printing the current byte to standard out. And in that node in the AST, it has a method, a private method. It says do print. And doPrint has an annotation on it, Truffle boundary. So that's how we tell Truffle, okay, these two methods, out.print, out.flush, you don't need to traverse during your partial evaluation. The second thing that partial evaluation allows us to do is to work with specializations. And specializations are a way to say, okay, let's take, for example, a language like JavaScript. Easy language, easy to make mistakes, because the plus sign can mean a lot of things. It can be addition of two numbers, can be concatenation of two strings, and I don't even know what it does if you have a number and a string. It's probably not a number, or undefined, I don't know, it's JavaScript after all. But there's a lot of implementations for specific cases in the JavaScript implementation. And Truffle allows you to provide highly optimized implementation for each of those situations. And we do that by indicating that a certain method is a specialization. Here we have a specialization for a divide operator. And we know that if the second number is unequal to 0, we have an optimized implementation. It's just A divided by B. It's optimized because we don't have to throw exceptions and do error handling and stuff. We just know that the division will always work. Or another example. Imagine we have an add operator. The add operator, given that both values are an integer, can either return an integer or a long. It depends on the outcome, because adding two integers may be bigger than the size of an integer. Now what we can do is we can have an optimized implementation there, which is add exact. And add exact has this behavior that it will throw an arithmetic exception instead of doing a type cast to a long. It's faster in the end. And what we say is there's a specialization for adding two numbers, but it needs to be rewritten when we catch an arithmetic exception. And then if we do catch the arithmetic exception, there's another specialization down there which will do the typecasting and give back a long value. So if we start running our program and we say, okay, execute it with a max value -1 and add the number 1, this should fit inside an integer, right? And indeed, we have do add no overflow, and the program runs fine. Now, if we want to add max value with the value of 1, this would overflow. This would not fit inside an integer. What happens? First, we invoke do add no overflow, which throws an arithmetic exception. And then the other specialization gets invoked, do add with overflow. Do add with overflow is more expensive because it needs to cast the result back into a long, which is bigger, etc., etc. But at least it works and it doesn't throw exceptions. So that's good. And then the next time we invoke this part of the AST and we would find an integer value which is, again, a max value -1, and we add the number 1, we still have the do add with overflow. Because Truffle has decided, well, this assumption that I did, this specialization that I used for having two integer numbers that do fit inside an integer, apparently it's no longer valid. Apparently, I can't trust this assumption anymore, so I'm going for my less efficient but still working implementation. So finally, earlier I said, yes, the GraalVM usually runs your program faster than a stock JVM. Why is that? Well, one of the reasons is that the GraalVM compiler knows about some Truffle instructions that the standard compiler on the Java platform does not know about. Here, for example, we are having an implementation for a function called abs, which is just absolute value of something else. Now, as long as we only have positive inputs, we have a very efficient implementation. We just return I. We don't need to do the negating the value because, yeah, you know, this is what you could say, this is highly optimized code. It does a few assumptions, but then it can run faster because it doesn't have to do complexer stuff. But in case we find one value which is not a positive integer, we invoke transfer to interpreter and invalidate. Transfer to interpreter and invalidate. That's a GraalVM specific instruction which says, okay, dear runtime, we used to be in compiled mode, but we're going back to interpreted mode now because I can't handle this. And by the way, the assumption that led you here, please invalidate that assumption because it's no longer valid. And then follows an alternative implementation which says if I is smaller than 0, return the negated value of I, else return the value of I. Now, a stock JVM does not know about these semantics, transfer to interpreter and invalidate. It will just, well, assume that it finally needs to run these instructions as well. Whereas the GraalVM compiler knows what this means. And it also knows that these instructions will not be executed anymore. So it can actually strip that away from the highly optimized machine code because it's never going to reach that one, and you'll be good to go. So the GraalVM implementations can skip out irrelevant code, which is just there because, well, at the end it needs to be valid Java code as well. But it knows about what that means and that you can strip that from the machine code that it generates. Now, we've seen quite a lot already from Truffle and how it works. Now, if we want to run our own language, for example, the Brainfuck language that I just showed you, or a DSL that you have been using inside your company, how do you actually approach that problem? Well, for any programming language, you have source code, usually, right? That's just a plain text file, lives somewhere on your disk, and it contains bytes. And the bytes, by convention, are interpreted as text. But that's a convention, after all. And the bytes might be, for example, 734 space dash space 692. Very trivial. To the human eye, we immediately see what's happening. But a compiler has no human eye. A compiler just sees bytes. So the first thing that we need to do is we need to do Lexing. And with Lexing, we start reading the bytes from our input and try to make sense out of that. So we try to assign meaning to groups of characters that we encounter. For example, the 734. Oh, well, that looks like a number. 3 digits in a row, that's a number. Yeah, that's a number, exactly. Okay, we create a token, which is basically those 3 characters together with a bit of semantics that tell, hey, this is a number. Please treat it as such. Then we have the space, we can get rid of that. Then we have the minus. Hey, the minus has a meaning in my language. So we create a token which maps to just this one character and say it has the semantics of being the minus sign, and then the same for the second number. And then the next step is that we do parsing. And with parsing, we have this whole sequence of tokens that we just got from our source code, and we try to convert that into a data structure. Parsers just say data structure, but if we're talking about parsing source code, it's usually a hierarchical data structure. And the hierarchical data structure in our example might be something like, hey, these 7 characters, that's an expression in my language. The expression is actually a subtraction, and the subtraction has 2 operands, 734 and 692. And now this is a very small hierarchical data structure which describes just this part of my source code. Anyone already calculated, by the way, what the answer is? Really? No one? It's 42. Of course it's 42. You could have known, right? So anyway, this gives us the hierarchical data structure that we call an AST. That one at the right there. So how do you build something like that? If you're like me, you're like, well, those are just pattern recognition things. You know what? I'll write some regular expressions. I'll just do a bit of pattern matching on my source code, and I'll be fine. And we all know what happens if you have a problem, and you start using regular expressions to solve the problem. you have one problem more than after you started. So for very simple languages, like for example Brainfuck, you might get away with this approach. If your language is more complex, please look at parser generators. A very well-known one is Antler, which allows you to describe the structure of the language and generate a parser out of that, which will do all the nasty checkings and all the nasty things that you really don't want to take care of if you really do this yourself, like I did in the first time. Now, okay, we have a parser, we can generate an AST from our source code, this is all excellent, but now we want to enable other people to run our language on GraalVM or even on a stock JVM. How do we do that? Well, GraalVM comes with an updater, the GraalVM updater, or GU for short, and it's a command line tool which helps you in installing components to your Graal installation. Components can be, for example, tools or language packs or basically anything. And generally, you just say a GU install native image, for example. Native image is a tool which is not shipped with GraalVM by default, starting with version 19. So if you want to run native executables from your Java source code, the first thing you do, GU install native image. This will look up the native image tool in some online repository. If your language is not there, like mine is, you need to add the -l switch, which says, don't do an online lookup, don't search online for this component. It's a local file and it lives here on my disk. Now, what does this component jar look like? It needs to have a specific structure inside. It's a basic jar file. There's a meta-inf folder, which has a manifest, of course, which is just the standard stuff you'll find in a manifest. Plus, it has one or two extra fields describing, hey, this is actually a GraalVM component, and this is the identifier under which it should be listed. You can define permissions and symbolic links inside your component using two additional files in the meta-inf folder, permissions and symlinks, which just say, okay, for example, here there's a BF, that's a shell script, which is a wrapper around this BF launcher. Well, the shell script should have executable permissions. That's something that goes in there. And then, in my case, I have a brainfuck.jar, which is the parsing stuff, the AST, etc. And there's BF Launcher, which is a very small Java command line program, which takes in a source file, reads it from disk, and tries to run it. And this launcher, as I said, you can invoke using the shell script that's in the bin folder. And this whole structure will then get extracted to your GraalVM installation folder. Now, if you want to run your language in a Java program, like in the Spring Boot application, as I demoed about 30 minutes ago, there's basically 3 steps that you need to do. First, you need to prepare your source code. You need to prepare a polyglot context. It's a Graal thingy. And finally, you need to evaluate your source code. Wow, excuse me. Better this time. So how do you do that? Preparing the source code is pretty easy. You can just read it from an HTTP request or read it from file or hard-code it inside your Java program. You invoke the source builder. You say, well, this is source code in the BF language. Here's the input. Build me a source object. Second thing you need to do is you need to prepare a polyglot context, which is also relatively easy. You ask the Graal context builder to create a context which allows you to run BF programs, which is the identifier that I chose for my language. And since we want to capture the output that our program generates, we first create a new byte array output stream. If we would not do that, the program would, when we have the dot, the print, it would print to standard out. But if we print to standard out, we can't show it in our web interface. So that's why we first have an in-memory output stream. We attach that to the context. So we tell GraalVM, hey, don't use standard out itself, but instead use this output stream. And then we build a context in that way. And finally, we have the context and we ask it, here's our source code, please evaluate that for me. Please run that. And after that has been done, we can ask the output stream that we created first and say what's inside. Please give that to me as a string. In this case, I did system.out.println again, but usually you would just give that back to your web browser, for example. Now, one other cool thing that you get when you run your programming language on GraalVM is that you have the option to use tools. GraalVM comes with a tool out of the box and allows you to write even more tools. And those tools will work on your programming language without much work from your side. For example, GraalVM ships with a debugger. I think we should make this a little bit bigger. What we see here is the annotated version of the program that adds the numbers 2 and 5, and we can see that this is, by the way, the Chrome debugger that you use when you debug JavaScript applications, for example. We can see that it just runs the whole program. It shows us the whole program, including the comments, and it actually recognizes that plus itself is just one instruction in the language. I can also look at the memory. In this case, you'll see that I have a memory layout of just 30 characters, not 30,000. That's basically because the Chrome debugger doesn't really like you to have 30,000 local variables. Every time you do stepping through your source code, it will hang for about 10 seconds, thinking about how should I display this. So I can just step through my program, one instruction at a time, and see how my memory is being changed by the instructions that I am executing. So at this point in time, we have allocated the value 2 and the value 5 into memory slots. And now we can continue program execution. Oh, well, there's a breakpoint over there. Now let's look. Hey, the program actually added the numbers 2 and 5 together, and it put it in the first memory cell, which has value 7. Now we need to do one more thing. If we would say print the byte 7 to standard out, I don't know, what's ASCII 7? That's not what we're interested in. We need to have the number 7, so we need to add 48 to the actual outcome in order to have the character 7. That's what this part of the program does, and then finally we can print it. Down there is, by the way, one special variable which I called __ data pointer, which is basically the pointer that tells you where you are in the memory array, right? So I can just continue program execution, and when the program is done, it will just quit, and my debugger is disconnected. No problem, that's what I expected it to do. That's a screenshot. Now the cool thing is that to have this working, the only thing you need to do is have a relation from your AST somewhere back to the source code. As soon as your AST knows, okay, there was a location somewhere in source code, line number so much, column number so much, this will work. And you don't need to write a debugger yourself. You don't need to know how to write such a complex tool yourself. You just tell GraalVM, this is where the source code lives, and this is a place where the program execution may be interrupted by the user, e.g. a breakpoint. You can write other tools as well, which don't ship with GraalVM at this time. And you use the instrument API for that. The instrument API is the basic toolkit for writing any kind of tooling, like code coverage measurement or profilers or whatnot. Anything that interacts with program execution. There's 4 types of events that this instrument API can emit to your tool, like source code being loaded, memory being allocated, language runtime or threads being created, and finally program execution. That's just, hey, I'm walking through my program, through my AST, I'm executing machine instructions, and this is where you could halt. So it's time for a wrap-up already. When I first heard about GraalVM and the fact that you can run any language on it, I was like, can you really run any language on it? Well, the answer is yes. Any language you can run with GraalVM. But it's not for free. You need to invest some time to get there. It's certainly fun to do so, by the way. I learned a lot about how GraalVM works. I had a few good conversations with people at Oracle that helped me out on really understanding how it works. And I can even think of situations where this might be profitable. There seems to be a large bank in the United States which have their own programming language, and they are considering to port their language to GraalVM. Well, if you have a large legacy code base on a platform that you wrote yourself, and you can now benefit from a highly optimized and very mature platform like the JVM, well, I can see how that could be profitable. So if you want to go down this path yourself, this is what you should take home. First of all, really, you don't need to write a parser yourself. There's many great tools that can do that for you. And maybe you don't even want to do that yourself, by the way, because it can be very complex. Just use already available tooling, because it's hard to beat them. Second, it's definitely worth your time to think about what the AST should look like. The AST design can basically influence whether your program runs correctly or not. If you make mistakes there, and trust me, I did, even for this very simple language called Brainfuck, you can think of a wrong AST design. Some programs may run, and some others don't. And it's very hard to find out why, until you think, well, maybe this spot in the AST is not what it should be like. I actually made a little tool for myself so I could visualize what the AST looked like, in order to track down if it really, if all the dots were connected in the right way. And the second reason why you should do that is that if you have a bug in your AST design and the nodes do not do what they should do, it's very hard to refactor the structure of the AST later on. As I said, it's a tree-like structure, and if there's fundamental flaws in how you designed the tree, it's hard to refactor that later on, and very time-consuming. Anyway, that's all I had for today. Thanks for being here. If you have any questions, we have a little less than 3 minutes left, or you can find me later during the day here. And please don't forget to rate the talk, because that's what helps making even a better Devoxx next year. Yes, a question. What are restrictions of GraalVM when it comes to reflection? That's your question, right? From what I've heard so far, it's very limited in what it can do in terms of reflection, because reflection basically allows you to invoke any method that was not there. It's not, you cannot deduce it from the source code, right? It happens at runtime, and that's what makes it so very hard. And that's actually what makes a project like Quarkus so impressive, because they actually tackle down that kind of stuff. If you write your own language, you typically don't have these kind of problems. At least my DSL did not have reflection, so that was pretty easy. But if your language does allow for that, yeah, that takes serious engineering to tackle that. And I think if you have the native image tool and you run it yourself, there's a way to say, okay, I know that it's hard to see at compile time, but I happen to know that my program will eventually run this or that method. Here's a file, and please consider that as input for generating the native executable. Does that answer the question? Yes. Excellent, thank you. Any other questions? You have just 50 seconds left, right? Okay, if there's no questions left, thanks again, have a wonderful day.